Okay, so let's start. Um, so this is week 9 of NPTEL course for Introduction to Astrophysical Fluids. Uh, my name is Rohan, and I'm a TA for this course. I'm a PhD scholar at ISC Bangalore, and yeah, so we'll start with a brief recap of the previous week, and then we will start with the material for this week. So in the previous week, we actually studied about, we ended with fluids in rotating frame. So we'll continue a bit on that, and then we'll start a new topic on uh, plasmas. Right? So we'll just introduce plasmas in this week, and maybe take it forward in the next week. So this is what we were doing in the previous week. So we started with stellar oscillations, which are basically, mm, you know, oscillations on the surface of the star, of any star. And so the way we studied about them is we introduced perturbations to the surface of the star, and then we solved the Euler's equation, uh, and we studied if those perturbations will basically grow in time or will they decay in time. And by taking linear perturbations, so we arrived at this equation dv dt equals to minus 1 by rho naught dp naught dr naught 3 delta gamma minus 4 by 3, where delta are the perturbations, first order perturbations uh, on the surface of the star. P naught, R naught, rho naught are the initial or unperturbed pressure, radius, and density of the star. So we argued that this is how the velocity changes with time, and if you know uh, gamma is greater than 4 by 3, we can see that dvdt will be negative, and therefore the perturbations will decay, and hence the star will be stable. Whereas, well, the stellar oscillations will be stable. Whereas, on the other hand, if gamma is less than 4 by 3, then the dvdt will be positive, and hence the perturbations will keep on growing in time, and they will be unstable. So after that, we went on to do the linear perturbation analysis, where I shared some material on the linear perturbation analysis, where we basically did linear analysis of the continuity equation, Euler's equation, and equation of state, and along with the gravitational force equation. So by doing the linear analysis, we got into the solution of those perturbations, which were in terms of spherical harmonics, YLM, and the solutions. And we finally saw that there are different modes of oscillations indicated by these numbers L and M. So the solutions were similar to that of the hydrogen atom equation in quantum mechanics. So if you have solved that, so we can separate the radial term and the azimuthal term, and then the azimuthal term will have all functions of spherical harmonics, which were basically Legendre polynomials and so on. And similarly, we will have different modes of oscillation in these uh, stellar. oscillations as well. Okay. So yes. So after that, we studied the Rayleigh condition for centrifugal instability. So we saw that uh, there could be stars which have solid body rotation. And by solid body rotation, I mean all the particles in the body will rotate with the same angular velocity omega. Right? Uh, or there could be cases where there are differential rotation within the star, where the omega varies with distance from the center of the star. So we studied in which case we will have solid body rotation, and which case we will have, this differential rotation, and when will this differential rotation be unstable. So basically, we derived that. So the way we did it was that we took two different shells at different radius within the star, and we assume that okay, some the first shell has radius r1 and angular velocity omega 1, second shell has r2 omega 2, and then we put a exchanged uh, volume of fluid between r1 and r2, and then we calculate the energy of the system in those two conditions, and then we saw which one has a lower energy, because the system will try to go back to state with lower energy. So if the system goes back uh, to the initial state, then we would say that that system is stable under differential rotation. Whereas if it doesn't, then we'll say that the system is not stable under differential rotation. And by checking that energy, we arrived at this condition that if omega 2 r2 square is greater than omega 1 r1 square, then the system is stable uh, under the centrifugal uh, stability, or under differential rotation, right? Whereas if this condition is not satisfied, then the system is not stable. So this is the really unstable region. Whereas this is the solid body rotation line. Okay. So yes. So below this line, omega 2 is basically greater than omega 1, and in this region, omega 2 is less than omega 1. So uh, below this region is what is happening is that the omega increases with radius, whereas between this region, the quasi-Keplerian region, the omega decreases with radius. Right. And this is also called the quasi-Keplerian region because this is similar to the Keplerian flow that we saw in accretion disk, is that the omega actually decreases with radius, whereas the angular momentum increases with radius. So omega has a proportionality of r to the power of minus 3 by 2, angular momentum has a proportionality of root r, right? So this also follows the same relation. Well, after that, so these are all the instabilities that we have studied so far. Like this is the end of our study of instability. So basically, we covered a lot of instability, starting from the source child instability, then moving on to um, well, uh, Rayleigh-Taylor, Kelvin-Helmholtz, right? Then gene cell instability caused due to gravitation, and I'm forgetting one more. Yes. Rayleigh-Bernard convection, of course, yeah. And then in the previous week, stellar oscillations, and then this centrifugal instability. So after we covered all these instabilities, and uh, we moved on to a different topic, a new one, which is the fluid dynamics in a rotating frame. So, in many times, so for example, even in case of Earth, when you do any measurement, the Earth is basically rotating, right? So when you do any measurement, we are actually not doing it in a lab frame, like you're not doing it in a stationary frame. You're doing it in a rotating frame. So it's important to understand what are the change in dynamics when we, um, you know, when we have a rotating frame instead of a stationary frame. So so we saw that the Euler's equation basically gets modified, and this is the omega cross r term, which is centrifugal term. So we'll have two more terms: the centrifugal term, and the other one is the Coriolis force term. So this is how the Euler's equation gets modified. So actually, I made a mistake in the previous lecture. So actually, I added an extra delta over here. So this term will not have a delta because we already have a delta outside the bracket. So I will remove this. Also the phi effective. So basically this equation tells you, so this is the left hand side is similar to what we had earlier. Del P by rho is also what we had earlier. Del phi is the gravitation term, also what we had earlier. Now this new term is basically the centrifugal force, and this is the viscous term also which we had, and this is the term due to the Coriolis force, right? So the only change is the introduction of the centrifugal force and the Coriolis force, and now we can see that the effective potential changes from phi to phi minus half of omega cross r. So here also this delta won't be there, right? Okay, so yeah, so this looks right. Okay, so right. So we saw that this potential due to the gravitational force is now modified and also contains the effect of the centrifugal force, and this is the effective potential due to the gravitational plus centrifugal force. And then we introduced another quantity, which is basically the ratio of the advective force and the Coriolis force. And if you do this calculation, this is proportional to V by omega L, where L is supposed to be the length of the system. So it just says that, if this is less than 1, so that means this Coriolis force is much higher, right? If it's much, much less than 1, that means the denominator has to be high. So this omega has to be high, or V has to be low. So in that case, the Coriolis force will be important. Right? Whereas if it's greater than 1, that means the top part is important and the Coriolis force is not important. And therefore, this top part you see is the numerator, is the advective term, and is a nonlinear term, which is basically causing this turbulence, which we studied earlier. And this Coriolis force is actually acting as a term which basically acts to decay these turbulence. Right? So yes, so that is the thing that is going on with this, and this is called the Rossby number. Okay. Okay, so if the Rossby numbers is very less than 1, then you have to consider the Coriolis force to be important. Whereas if it's much greater than 1, you can neglect this Coriolis force. Okay, vorticity in the rotating frame. So again, okay, so here also I have made this term. Okay, okay, just correcting this. Right, so this is the same equation as this one. And now, if you remember, when we were calculating vorticity in a normal stationary frame, we were just decomposing this term into this thing, and where omega is del cross v, which is the curl of the velocity field. So how will it change in presence of when we do it in a rotating frame? So basically del v del t. So if we decompose this term, del of v square by 2, which is taken inside this gradient overall. And this is how the equation turns out to be. And from there, if we take the curl of this equation, this is how the equation looks. And we say that del omega del t is equals to del cross v cross omega plus 2 capital omega. So this omega is the rotation angular velocity of the rotating frame, and this omega is the vorticity within that, uh, with respect to that frame. So we can again rewrite this equation like this, and this just says that, even if in the initial system you have no vorticity, but because of this term, the rotation of the frame, it will introduce some vorticity inside the fluid, right? Even if we start with an initial vorticity 0. And this is how the circulation theorem changes. So earlier with capital omega 0, we only had that the vorticity was constant uh, within a loop. But now, no, the omega is not constant, but the omega plus 2 capital omega, the whole summation is constant within a particular loop. Right? Okay, so right from there, we studied one important theorem, which is the Taylor-Proudman theorem, and which states that, so if you go from this equation, if we take it to be in steady state, so this gives rise to this thing, right? And if if the vorticity is much less than the angular velocity of the rotating frame, so then we can neglect this one. This equation reduces down to this, and then we derive that this is basically equals to this under the assumption that it's a steady ideal incompressible fluid in rotating frame, right? So we also actually showed how to get from here to here. But this equation has some physical implication, which we saw in the previous week. So we saw that what this states is that the velocity, the change in velocity or the gradient in velocity along the direction of omega is basically 0. So that means v is constant along the omega or the rotation axis. So then we saw that in an experiment that when you have a jar of water, and the fluid is rotating in that jar, and you introduce some perturbation or some obstacle at the bottom of the jar, and then the fluid will make way around that obstacle, right, at the bottom. But okay, so whether coincidentally you see that although there is no obstacle present at some height, the fluid will still follow the path that is followed by the fluid at the bottom, right? As if there is some invisible obstacle present over there. And why is that? Because the velocity cannot change along the z direction, which is the direction of the rotation axis, right? So the velocity will be same in that column, which is basically called as the Taylor column, right? Okay, so that's what we did till last week. Let me know if you have any questions. Okay, so now this week, as I said, we will continue some of the discussions that we were doing in the previous week about uh, fluid in a rotating frame, and we will study the effect of rotation on a self-gravitating mass. So, for example, what if a star, you know, is rotating, right? So, what will be the effect of that rotation on the star? And then we will move on to plasmas. Right? So, right. Okay. So this was the equation. Okay. So this was the equation, modified Euler equation in presence of rotation. And if we break it down, then we will get to this, right? So, up to this we have done till previous week, right? By just decomposing v dot del v in this way and just putting it over there, and then taking v square by 2 within the gradient and also p by rho within the gradient, we get to this equation. Okay. Now we want to see how this equation will behave when velocity is 0, right? So if we assume that v is 0, so note that this velocity, this v, is the velocity with respect to the rotating frame, right? So we are assuming that although the frame is rotating, but with respect to that frame, the fluid do not have any velocity. Okay? So that means the fluid is rotating with it. So if we assume that, then what this term will go to 0 because v is 0. Here also v is 0. Here also v is 0. And here this term will go to 0 because v is 0. So we're left with this equation, right? So this just means that, del of this thing is 0. That means the inside this quantity is basically constant or just a function of t, right? Now what we do is that we focus on the outer surface of the star, let's say, which is rotating. Now at the outer surface, pressure is 0, right? Because at the surface, at the center, you have the highest pressure, and as it goes on the surface, because there is no matter, like density goes to 0, therefore pressure also goes to 0, right? So this term, the first term, will go to 0, whereas what remains is the rest of the equation, which is phi minus half omega square x square plus y square equals to ft or some constant, right? Now, well, this is the equation of an ellipsoid actually, and we will see how this is an equation of an ellipsoid. So, but if you try to visualize it, from just imagination, is that when you have some body which is rotating, right? So you can imagine that it will form something of this oblate kind of structure, right? So for example, even our Earth is not exactly spherical, right? Because of rotation, the equators will have larger circumference, whereas the poles will have a um, smaller circumference if you go through the poles, right? So this is the oblate kind of a structure which is generally formed when you have some body which is rotating, right? So the opposite of this is this pole-like structure, which will be larger circumference in the pole, smaller circumference in the equator. But yeah, we'll be mostly focusing on this oblate structure. But here, you know, I mean, in Earth, uh, the equator, so if you just imagine an XYZ axis uh, on this oblate structure, so let's say X is your this direction, Y is out of the plane, and Z is vertically up direction, right? So, well, sorry, X is the coming out of the plane, Y is on the right side, Z is the going vertically up, right? So in that case, you can like imagine that uh, the this structure will have same length in the x and the y direction, right? So if you consider the the intercepts as a, b, and c along x, y, and z directions respectively, so you can imagine that a equals to b, but which is greater than c, right? But actually, in the most general case, A might not be even equals to B, right? So that could be the most general case, uh, which we will see. Uh, I mean, why would some system choose the uh, A equals to B, or A not equals to B not equals to C? So those are the cases, like when A not equals to B not equals to C, those are the cases which are called ellipsoids. And when A equals to B, but not equals to C, actually greater than C, in those cases, those are called spheroids or Maclaurin spheroids in this case. So we will also see in which case the rotating self-gravitating mass will take the form of a spheroid, and in which case it will take the form of an ellipsoid. Okay. But let's just assume that this takes the form of an ellipsoid, and this is the equation of an ellipsoid: x squared by a squared plus y squared by b squared plus z squared by c squared equals to 1. So this is similar to an ellipse with a uh, z component as well. Right? So this is the equation for the boundary of the surface of the star or whatever. Now, what we can do is that so this is an ellipsoid whose equation is given by this, and we can actually find the gravitational potential because of this ellipsoid at any point xyz, let's say. Okay. So it's just like how we calculate gravitational potential for any object, right? So it's integration of gdm by r square, right? And integrate over all r. So it will be it will calculate the well gdm by yes. So it will basically uh, calculate the potential due to each uh, elemental mass uh, that is inside this ellipsoid. And if we integrate over the whole ellipsoid, we'll get the gravitational potential due to this whole ellipsoid at any point outside whose coordinates are x, y, z. And that potential turns out to be of this form: pi g rho alpha naught x square plus beta naught y square plus gamma naught z square minus chi naught, where rho is assumed to be the constant density of the ellipsoid. And alpha naught, beta naught, and gamma naught are actually given like this in terms of A, B, and C, right? And chi naught as well. So where delta is given in terms of C. So if you see all these alpha naught, beta naught, gamma naught, and chi naught are basically integrals over lambdas. So since they're integral over lambdas, the after you integrate, the lambda will vanish, right? 0 to infinity integration. So they will be some function of A, B's, and C's, right? Only the A, B, C term will remain. So these are actually taken from this book, which I have also mentioned in reference. So these are taken from the book by and yeah. So look at this book, and You can find it there. Okay, so right. Now another thing is that also you can express this alpha naught, beta naught, and gamma naught in terms of the eccentricity of this ellipsoid. So, in case of spheroid, as I was saying, the eccentricity can be defined by root over of 1 minus uh, c square by uh, a square or b square, because a and b are equal. So, yeah, it's written over here, 1 minus c square by a square. And that's how you can also get alpha naught, beta naught, gamma naught, chi naught in terms of this eccentricity E, right? So we'll see how, why that is important. So, okay. So before that, as I was saying, that this phi can be expressed in terms of these parameters. And yes, so right now phi is also this thing plus some constant, right? So if you look at the equation at the outer surface, now combining these two, we get this equation: alpha naught minus omega square 2 pi 0 x square plus beta naught minus omega square 2 pi 0 y square plus gamma naught c square equals to constant. Right? We just put the value of phi over here, right? And we'll get this equation. So this is the equation of the outer surface uh, of the ellipsoid, right? Because this condition is only valid at the outer surface where pressure is equal to 0. And we put the value of phi over here, and we get the equation for the outer surface. Right. So now we compare this equation with this equation, where this is the equation of the for the ellipsoid, right? So from there we can get this equation just by comparing the coefficients of x square, y square, and z square. So x square coefficient is this thing, and here is the coefficient is 1 by a square, right? So this times a square will be equals to this times b square equals to this times c square. Okay. So that both the equations are valid. Okay. So this we did, and then we also know how to express alpha naught, beta naught, gamma naught in terms of ABCs and eccentricities. And finally, you see, so basically these equation are basically contains omega and alpha naught, beta naught, gamma naught, and ABC, right? So if we can express alpha naught in terms of eccentricity, also we can express AB in terms of ABCs in terms of eccentricities, right? So basically, from here we can see that we can also express this function omega square by pi g rho in terms of eccentricity, right? And this is how the expression will turn out to be, right? So what does this mean is that so if we just plot omega square by pi g rho as a function of eccentricity, right? So this is how the plot would look like. So what does this physically mean, right? So you see that as omega increases, the eccentricity of the spheroid or ellipsoid will increase, right? So which seems natural, right? Because the more you rotate, or with more angular velocity you rotate some object, it will be more elliptical. But then it doesn't increase forever, right? So it increases up to a point which has a maximum omega, whose value is around 0.449, right? and after that it suddenly drops, and this is at a very high eccentricity, around zero point 0.9 or larger, right? So right, so what is happening here? Like, why is the eccentricity decreasing suddenly after uh, after uh, after some certain value of omega, right? Because g is constant, pi is also constant, rho is also constant if we consider a constant density of the mass, right? So this omega increasing with eccentricity and then suddenly dropping. So here, to analyze more, we actually look at the angular momentum of the system. So this L is and the angular momentum. This for a sphere, it's 2 by 5 ma square, where a is the radius, and this is the I, the moment of inertia, I times omega. And this mass is given as 4 by 3 pi a square c rho. Uh, so this is the volume of the spheroid. Okay. So right now we are all dealing with spheroids, which is a equals to b, not equals to c. We are still not into the general case of a not equals to b, not equals to c. So this is the mass of the spheroid, and this is how it is. So we put the mass over here, and we calculate this L, and then we calculate another quantity which is normalized L, which is just to make sure that the units that this quantity is dimensionless, and this turns out to be of this form. So this depends as well. This is how this quantity is. Now we plot the angular momentum, this normalized angular momentum with eccentricity again. And here we see that the angular momentum keeps on increasing forever. Right? And unlike the omega, the angular velocity, which decreases after a certain point. So what is going on over here is that, so angular momentum is I omega, right? So why is omega decreasing after a point, but angular momentum keeps on increasing is due to the fact that angular momentum is directly proportional to omega, but angular momentum is also directly proportional to the moment of inertia, I. So after a certain point, although the omega is decreasing, but the I, the moment of inertia, is increasing by a rapid amount. Like the moment of inertia, the increase in moment of inertia is basically dominating over the decrease in omega, right? So omega is decreasing by some amount, but the moment of inertia is increasing by a larger amount over there. So that is what is causing this angular momentum to increase more and more with eccentricity. So okay, now the question is that we stated earlier is that in which case uh, will the system not be uh, a spheroid, but will transition into a uh, ellipsoid in general. So till now we have studied all cases which has a equals to b but not equals to c. But this is the equation of an ellipsoid, a general ellipsoid where a not equals to b not equals to c, right? And it states that if the dimensionless angular momentum, so this L bar, is less than 0.304, which is corresponding to an eccentricity of 813, so somewhere over here, right? Then Maclaurin spheroids are the only possible solutions, right? Whereas if this eccentricity is greater than 0.813, or in other words, the angular momentum is higher than 0.304, uh, you know, so only when the angular momentum is increased beyond 0.304, a Jacobi ellipsoid with three unequal axes becomes a possibility, right? So basically, you have to calculate the angular momentum of the system and see if the dimensionless angular momentum is greater than that. Then the system will no longer be a spheroid, but well, it could be a spheroid, but it could also be an ellipsoid. But if the angular momentum is less than that value, 0.304, then definitely uh, ellipsoids are not possible, because as you can see, Maclaurin spheroids are the only possible solutions. Okay, so that is it for effect of rotation. Now we'll study about what effect does the rotation have on stars, or do they really have any effect in stars or not, right? Or what is the magnitude of this effect in stars compared to other effects? Or in other words, like will it matter if we you know uh, neglect these effects or consider these effects while solving the equations for the stars? So again, let me correct this equation, and here also. Okay, so right. So this is again the Euler equation in rotating frame. Right? This is the phi effective, right? And we basically now consider again we consider velocity to be zero, right? And yes, so if we consider velocity to be zero, this term cancels, and the last two terms also cancel. So we are left with only del p by rho uh, is equals to del phi effective, right? So this is the effective. And note that the velocity zero means only with respect to the rotating frame, right? Uh, I'm just mentioning that because the star is rotating with respect to you, but um, with respect to the rotating frame, there is no motion of the fluid inside the star. So the star do have motion with respect to a stationary observer. So yeah, so this is the equation that we get, and from there, if we take a curl of this equation on both sides, right? So this equation will reduce down to this thing. So I can just quickly show the curl uh, condition. Open the whiteboard. So the equation we had was del p by rho equals to minus del phi effective. And if we take a curl on both sides, so curl of gradient is zero, right? So this term will be zero because curl of gradient is zero. But here we will apply chain rule. So this will be rho square rho del cross del p minus del rho cross del p equals to zero. So again, we have a curl of gradient over here. this will go to 0, and if we transfer rho squared to that side, we are just left with del rho cross del p equals to 0. Right. Now the analysis that we are going to do after this, like we want to understand what this equation means, right? So let's say that you have a surface, right? So this surface is within this is basically an imaginary surface within the star, let's say. Okay. So this is the whole star, and if you consider any surface within the star, so let's not consider any surface. Let's consider a specific surface, and those specific surface is this surface is basically a contour of let's say P pressure contour. So that means all points on this surface have the same pressure, right? Now del P, when we calculate del P, this term del P will actually point perpendicular to the pressure contour surface. So this is perpendicular, normal to the surface, right? Similarly, if we construct rho surface, constant rho contours, the perpendicular to that constant rho contours will be basically be given by del rho, right? So, let me just show them. So if you have, so these are the surfaces where density is constant. So del rho would be along this region. Note that these surfaces could be different, right? But when this condition is satisfied, what this condition is saying is that the del rho and the del p are basically parallel, right? So cross means sine theta, right? So del rho del p sine theta equals to 0. So this theta has to be 0. So that means that the angle between del p and del rho should be same, right? Or in other words, the del p and the del rho surface, the constant p and the constant rho surface are the same surface basically. So if you take the surface of constant p, on that surface, the density is also constant. Right? So that's what this uh, relation actually means. Okay. Okay. So that's what I wanted to say for that. Right. So, right. So contours of constant p and rho are either parallel or coinciding. So that's what we saw. So which will also be parallel to the contours of constant phi effective, right? Why? Because of this equation, right? So del p is equals to del phi effective. Well, this rho is just a constant, so del p is proportional to the phi effective, right? Del phi effective. So phi effective is also, coinciding with p and rho surfaces. Well, for ideal gas, we know P is P equals to rho RT. So if P surface is equal, R surface, rho surface is equal, then P should also be constant along in that surface, right? Constant P surface. So we see that if we construct a constant P surface, then density will be constant, phi effective will be constant, and temperature is also constant. And all these surfaces will be spheroidal, right? So, for example, like we saw in this cartoon diagram, that these will be mostly like the contours in this surface along which the pressure and those things will be constant. So, for example, if you look at the surface, so this is the pressure contour, which is zero. Right? Similarly, we will have inside, we'll also have some such surfaces where pressure is constant and so on. So one thing to note is that since this is spheroidal, so there will be more contours uh, towards the poles, because the shape is an oblate shape, right? Whereas we'll have rarer contours near the equator, because there's a bulge at the equator and the equator is more spread out, right? Uh, Whereas the poles are less spread out. I'm just saying the contour density will be more at the poles. Now, what we want to do is calculate the radiative flux. So by radiative flux, so if you remember the energy equation, right? So the energy equation was um, del E del T, where E is the internal energy, plus the change in kinetic energy and so on. And then you have a kappa delta T term, right? Which is the heat flux term, right? So that is basically what we are referring here as the radiative flux term, and that is proportional to delta T, which is the change in temperature. Now, as I said, you will have more density of contours at the poles. So therefore, delta x will be shorter at the poles, right? So del T del x. So if delta x is shorter, the radiative flux or gradient of T will be larger at the poles, and hence the polar flux will be much, much larger than the equatorial flux. So, so this is what we obtain from this theory, right? Now, any good theory needs to be tested with observations. Now, the question is, what do we see from the observations? And it turns out that the radiative flux that we measure from this theory do not match with the nuclear generation rates that we see, right? And this is what is called the Zeipel paradox, right? And well, there are some technical details on how this, uh, you know, uh, how this paradox is resolved. But the main idea is that, this rotation of the stars turns out to be not a very good approximation in case of, the rotation effect is not contributing much to the observations. And rather, if we consider the star neglecting the rotation effect, those theories give results which are more closely matched with the observations. Right? So the bottom line is rotation effect in stars do not give much impact. Right? But that's not all actually, because uh, then why would we study the effect of rotation in stars? Turns out that there could be one case where this rotation effect uh, might might be important, and that is the case of a collapsing star. Right? So we all know that the stars are formed from this sorry, the nebular clouds, cold gas in the interstellar medium, and when this gas uh, falls under gravitational collapse, we already studied about Jeans instability, when uh, the condition when the gas will collapse on its own and it starts nuclear burning, and then the star burns hydrogen, after that helium, and after helium is exhausted, it goes into carbon, nitrogen, oxygen, and finally it goes to the most stable element, which is iron. So at the end uh, of very massive stars, the core of the stars will be consists of iron. But what happens after the star has burned all of its fuel? well, actually, lower mass stars will not even go to the stage of formation of iron. They will collapse even earlier after it has lost all its fuel. The star will collapse under gravitational pull when the nuclear fuel is exhausted and the gravity actually dominates, and the star will collapse into, depending on its mass, it will collapse into a neutron star or a black hole, right? So yes, so that is how the stars actually collapse. Okay. So yes, now but why we are actually studying this? We are studying this because we want to see where the rotation effect will be important, right? So let's see what happens in case of a collapsing star, whether the rotation effect will be important or not. So, okay, so moment of inertia for a rotating star or any object basically is proportional to a square, right? A is the radius of the star, let's say. Now, when the star collapses, the radius decreases, and therefore uh, the moment of inertia decreases. The angular momentum actually is proportional to e to the power of minus 2, right? So this comes from the conservation of angular momentum, right? So, well, the angular momentum isn't proportional to 8 to minus 2, but well, if you consider conservation of angular momentum is I omega. So I omega before and after the collapse will be conserved. So that means the omega, well, since I varies as a square, omega will should vary as 8 to the power of minus 2. So therefore, omega will increase, right? Because I is decreasing. To conserve the angular momentum, omega has to increase, and it varies as 8 to the power minus 2. Now we can calculate the centrifugal acceleration. Okay. So now what we are trying to see is that the competition between the two forces, the centrifugal force and the gravitational force, and we're trying to see whether which of these two terms will dominate. So from here, if you see, okay, so for stars, if we just neglect the centrifugal force, it just means that phi effective will just be phi. You are just neglecting the second term. But we want to see when this term will be at least equal or greater than this phi term as well, right? So this phi term is coming from the gravitational acceleration. This term is coming from the centrifugal acceleration, right? So centrifugal acceleration is omega square r, right? So omega square a. Here the radius is the a. So if you do omega square a, so this will be a to the power of minus 4 times a, which is 8 a to the power minus 3. So centrifugal acceleration is actually increasing as the star collapses, and a is decreasing, centrifugal acceleration increasing, and gravitational acceleration, which is again proportional to 8 to the power minus 2, which you all know, is actually also increasing. But you see, the thing is that which one is increasing or decreasing more uh, rapidly in terms of a. So if you see, this centrifugal acceleration has a power relation of 8 to the power of minus 3. So therefore this will increase more than the gravitational acceleration, right? So that is the catch here, that there will come a time, or there will come a radius or a value of a at which the centrifugal acceleration will dominate over the gravitational acceleration. Right? And that radius is given as, well, to just calculate, uh, okay, so this is not that radius, but so, okay, so we are coming back to this diagram, right? So if we saw that omega square by pi g rho has a maximum value of 0.449, so this peak value is 0.449. Now, this is the condition that needs to be satisfied, right? Because if the centrifugal acceleration or the omega increases over that value, then the star will, dispose matter outside, right? So that is the maximum limit of omega. So omega square has to be less than 0.449 pi 0, right? And this is the condition that always needs to be satisfied. Otherwise, the star won't be stable. So we are trying to calculate what should be the maximum omega that the star can reach, or the maximum time period of the star. So from omega, we can directly calculate the time period of rotation, which is 2 pi by omega, which is just given as like this. Okay. And for white dwarfs, this is the typical density of the star, 10 to the 8 gram per cc, and it turns out that the time period of those stars are 2 seconds. Whereas for neutron stars, this is the typical density, and turns out the time period are 2 to the 2 times 10 to the minus 3 seconds. So these are very rapidly rotating stars, right? And these neutron stars actually emit uh, radio signals or pulses, which are actually called pulsars, right? And there are, if you notice these are of the order of milliseconds, and hence they are called millisecond pulsars, which are actually a um, current uh, topic of research, right? So there are these pulsars which emits these pulsars which you observe from Earth, and we try to study their dynamics, like how fast they are rotating and what should be their composition and all the different things based on the signals that we receive. Right? Right. So these are some of the things uh, that we can do, and these are the some of the regimes where the the rotation of the star becomes important. Right? Okay. So this is the end of uh, effect of rotation in stars, or effect of rotation in fluids. Uh, Now we will start a new topic, which are called plasmas. And before that, so we will just take a short break. And after the break, we will start with theory of plasmas. All right, so let's get back. So yeah, so we'll be starting a new topic, which is called plasma. Now, till now, we have studied fluids, and now the question is, why should we be studying uh, plasma, and what are its importance in astrophysics? So, in astrophysical context, plasmas are the most abundant, uh, well, matter there is. And as you see that plasma is the fourth state of matter, which we have studied in high school, right? And it turns out that uh, 99% of the matter that is present in our universe are basically plasmas. Right? So they are the most abundant uh, matter in the universe, and that's why these are the most important in astrophysical context. So for example, like we have studied accretion disks, right? So the you know the matter that is falling in the accretion disk is actually not a fluid, but it's actually a plasma, right? So why is it a plasma? So that we'll see why. So if you see the states of the matter, so for example, we start with the solid, right? So for example, you heat up a solid, let's say ice cube, and then it will melt into a liquid, water, and then you continue heating up the water. It will vaporize into water vapor in the gas state. Now, what if you heat up the gas even further? So what will happen is that the gas molecules will break apart into um, hydrogen and oxygen. And if you keep on heating those molecules, uh, they will, ionize. By ionize, I mean they will disintegrate into ions and electrons. So, for example, hydrogen has one electron. So, if we keep on heating it, it will, release one electron because of the thermal energy provided to the atom. It will release one electron, and that electron will be free, whereas H will be an H plus ion. So this ionized gas is basically what is called the plasma. And well, you see in this diagram, right? So these are the molecules in the gas, and as you keep on heating, the molecules will. So till now, this is the gas molecules, right? And in that you have a nucleus and the electrons, bound electrons attached to it, right? So you will have multiple molecules like that. But if you keep on heating it, the electrons will become free. It will no longer be bound to the nucleus of the atom. And this is what a plasma looks like. It's a mixture of ions and electrons, basically, right? Or an ionized gas, whatever way you look at it. Right. So now, as I was saying, in accretion disk, for example, the temperatures of the accretion disk is of the order of 10 to a 6, 10 to a 7 Kelvin, and at least, and it can go even higher depending on what type of accretion disk you have. So, at those temperatures, all the gases are basically ionized, and they have ion and electron, which will have two distinct temperatures uh, in the same plasma. So, for example, as I was saying that you have these ions and electrons separately, and these ions and electrons will have separate properties also in the plasma. And by separate properties, I mean they can have separate temperatures, they can have separate velocities, or so on, right? So they will have different properties, right? Different temperatures, definitely, right? So that is the property of, and also different velocities, and all the remaining properties will be different for this ions and electrons. Okay, right. So that's why this accretion disk material is often modeled as a two temperature plasma, because one for the electron, one for the ions. Okay, so now what we are going to do is that we'll see some properties of plasma. Okay. So this this system of plasma, we are going to consider it as having some you know ions, and within that background of ions we will have some electrons. So that's how we are going to model it, and we are going to see some properties. So we just want to derive the Debye length of this um, plasma. Okay. So before that, let me just motivate you physically, like what this Debye length means and what it physically signifies is that. So you have this, as I said, ions and electrons moving around, and so when you have this ions, well, also that there has to be some charge neutrality, at least globally. So whatever the number of ions are, the number of electrons should also be same, right? So for example, in case of hydrogen has only one electron, which is going to give that electron, and so the number of hydrogen ions will be equal to the number of electrons in the plasma, right? So charge neutrality is maintained. Number of positive charges is equal to number of negative charges. But if you look at a local scale, very small length scales, let's say around the ion, for example. So the ion has the positive charge, right? So it will attract negative charges, or it will attract electrons towards it, right? Similarly, electrons will repel other electrons, and ions will repel other ions. And so inside, at a local scale, there would be some length scale at which the ion will accumulate many electrons around itself, right? And hence, in that length scale, the charge neutrality is not valid, right? Because the net charge will be negative within that length scale. So we want to study what is that length scale, and that is actually what's called the Debye length or Debye shielding. So because the ion is shielding um, itself with these electrons. Okay, so as I said, we will model the plasma as having a background uh, ions, background number of ions, and the number density of ions is n naught, let's say. And within that, we'll have some electrons whose number density is Ne, right? So this is just the uh, Gauss law for uh, from electromagnetism, right? So we know that del dot E is rho by epsilon naught, and so E is electric field, and E is basically del phi, gradient of phi. So del square phi is equal to minus rho by epsilon naught, right? And rho is basically the charge density. So charge density is the charge times the number density, right? So this is given as E of n naught minus Ne. So n naught has positive charge, Ne has negative charge. So n naught minus Ne, epsilon naught. Now, okay. So now we assume that the that the distribution of ions and electrons in the plasma follows a Maxwell-Boltzmann distribution, right? So we all have studied Maxwell-Boltzmann distribution in the starting from the first and second week lectures. So this is how the Maxwell-Boltzmann distribution looks like, but there is one extra factor of Q phi along with the mv squared term, which is because of this uh, additional, uh, you know, additional force over here. So along with, so when we derive the Maxwell-Boltzmann distribution, we do not have any electric field present over there, right? So you only had all particles moving freely in a thermal medium, right? So now in presence of electric field, so there should be another extra energy along with the kinetic energy, right? And the energy due to the electric field is given as Q phi, where phi is the this potential. Right? So this is how the Maxwell distribution will get modified in the presence of an electric field. So now what we just see is that therefore Ne coming from this Fe is just N naught. So if you just ignore the electric field over here, so the remaining term will just give you the N naught e to the power of minus E phi by kT. Right? So N naught, okay, so another assumption that we are also following, as I said, that we consider the background to be filled with ions, and within that we just insert these electrons. Also, since ions are more, ions are heavier than electrons, much heavier than electrons, right? So we consider them to be static. We don't consider them to be, attracted towards the electron. So when you have a heavier mass and you have a smaller mass, the smaller mass will come to the heavier mass, right? So in a similar way, we consider the ions to be static in their position, right? And the electrons will be moving around freely within that setup. So the background number density is basically this thing, the N naught, and this is how the electron number density would vary, right? N equals to N naught e to the power of E phi by kT. Now, what we do is that we put the value of Ne over here, right? And this is the equation that we obtain: M naught E by epsilon naught 1 minus e to the power of E phi by kT. Okay. So remember, as I was saying, that the temperature of the ions and electrons will be different, right? So here, if you notice that I am mentioning TE, which is the temperature of the electrons specifically. So we are only doing this analysis for electrons, right, for now. And then we'll see that we can do this for any species. We can do the similar analysis for any other species. So for example, you could have multiple species in the plasma. So for example, you could have hydrogen ion, oxygen ion, and so on. Right? So you can do the same for each of them. Okay, so this equation got reduced to this equation, right? And now what we do is we take one assumption that E phi by kTe is much, much less than 1. So this exponential is very small. And we will see in the next slide that what that assumption means, like what is the physical significance behind that assumption. But right now, let's just assume that this exponential power is very small. So in that case, what will happen is that if we just expand this in binomial series, e to the power of x is 1 minus x, plus x squared by 2 factorial and so on, right? So we will just expand up to the first order, so 1 minus x, right? So that will give me 1 and 1 will cancel, and there will minus e to e phi by kte, which will become plus. So here it is n naught e square phi by kte and epsilon naught on e square. So this is how the equation reduces if we have a uh, small approximation. Okay. Okay, so this is the equation that we get. Now what we do is we just expand del square in spherical coordinates, right? So del square is del r square of r phi equals to this thing. So this is just in spherical coordinates. So there will be, yeah, 1 by r also over here. Okay. Right. So that r will come over here. Now this is a simple second order differential equation, and this has a solution of this form: phi equals to a by r e to the power of minus r by lambda d. Now you can also do it in this way, that you just put this value over here. So let's just do this and let's just see what lambda d is, and then we'll study the physical significance of lambda d. So let's see, we have some space. So let me see what the equation is. Okay, so right, so this is the equation, and we are saying that okay, this follows this thing. Now just to check if this really follows this thing, we're just going to put the value of phi over here, right? So this will turn out to be del r square. Phi is a by r, so the r will cancel. So this will be a e to the power of minus r by lambda t minus n naught e square by epsilon k t e of e to the power of minus r by lambda t equals to 0. Right? So a is constant, so we can cancel this a with this. And what is double derivative of e to the power of r by lambda d? So the double derivative with respect to r is 1 by lambda t square e to the power of minus r by lambda t m naught e square epsilon k t e equals to 0. Right? Similarly, we can also cancel e to the power of minus r by lambda d with e to the power of minus r by lambda t, and therefore lambda d square equals to epsilon naught k t e by m naught e square, or in other words, lambda d is root over of this quantity, right? So this is lambda d, and this is what is called the Debye length. Right? Now, what is the physical significance of this Debye length? If we just want to see from this equation, let's say, so this just says that, you know, if we have very small r, right? So if r is very small, then this term will be very high, right? Now, after a certain radius, as we keep on increasing r, this term will go on decreasing, right? Because, well, so if we write it like this, phi equals to a by r e to the power of r by lambda d. If we go on increasing r, this term will increase, this will also increase. And so therefore, the phi will decrease, right? But, you know, this is an exponential term. This will, after a certain r, the exponential will dominate over this linear term, right? So at high R, let's just focus on the exponential term, and it just says that if R is much less greater than lambda d, the potential will go to zero. The electric potential will go to zero. So that means there will not be any, effect due to the electric field when uh, R is much greater than lambda d, which is the Debye length, and therefore it means, since electric field effect is not there, that means there will not be, shielding effect due to the individual ions that I just mentioned. That, at a local level the ions will accumulate the electrons, but at the global level, and by global I mean R much greater than lambda d, at that level the electric field will play a negligible role and charge neutrality will be held. Right? So yes, so if we just consider a single charge of charge q, the phi will reduce down to this. Like this just comes from the condition that at r equals to 0 there is a charge q. Right? So right, and this lambda d will turn out to be something like this. So lambda d depends on the temperature and the number density of ions, right? And so if you increase the temperature of the system, the lambda d will keep on increasing. Or if you increase the density of the ions, lambda d will decrease. Right? So that is the take from here. So also you can see from this thing. Right. Okay. So we're gonna, study about one more concept, which is the plasma frequency. Then we are going to study about uh, criteria for plasma. So basically, it means that when can you say that, okay, this matter is in the plasma regime, right, and not in the fluid regime? When can you treat something as plasma or not? Right? And finally, we are gonna see when does the quantum mechanical treatment of these plasma become important, right? Because there are many literatures which actually uh, talk about quantum mechanics of this plasma, quantized plasma, right? And those are actually important in some astrophysical scenarios when you have to treat the plasma in a quantum mechanical way and not a classical way. So I just mentioned those cases, and yeah. So starting with plasma frequency. So what does it mean actually? So if you can look at this figure, right? So we have a box of plasma, let's say, and now what you do is you displace this box a little bit. You just perturb this box a little bit such that we have some density of electrons. So inside this, everything is neutral, right? Now, let's say that charge neutrality is violated because in a plasma, there will be some perturbations because the electrons are separate from the ions and so on. So you just perturb the system a little bit such that, the electrons the electron density becomes higher in this region, whereas the ion density becomes higher in this region 1. And this perturbation length is of delta x. Now, what is the electric field that is uh, getting generated because of the separation of this positive and the negative charges? So this electric field is basically given as n naught E delta x by epsilon naught. So this is similar to a capacitor, right? So you have studied in your electromagnetic course that a capacitor has a positive charge on one plate and negative charge on the other plate, and there's an electric field in between the capacitor, which is given by this thing, n naught E delta x by epsilon naught, where n naught is the density of the positive ions, which is also equal to the density of the electrons. Right. So this is the electric field that is getting generated, and therefore, because of this electric field, the ions and the electrons will experience a force which is proportional to this electric field multiplied by the charge of the ions of the electrons. But like remember, as we said in the previous prescription as well, that we are assuming that since the ions are heavier, they are stationary. So therefore, it's the electrons who are moving towards the ions. So we just apply Newton's laws, and therefore Newton's laws for the electrons is mass times acceleration equals to force on the electrons is minus E times the electric field. And it is this. Now, well, so this equation gets reduced down to this equation simply by taking the mass on this other side. And now if you see, this is an equation which is basically the equation of a simple harmonic oscillator, right? So double derivative of some quantity is equal to the negative of that quantity, right? So the solution of this equation is given as a sinusoidal wave, right? So let me just show you here. So the equation is del 2 del x del t square equals to this, right? So del x will be a sine omega t plus b cos omega t. Right? So this is the solution of this differential equation, because if you take double derivative of sine, it will give minus sine, and double derivative of cos, it will give minus cos. And that is what is happening over here. And this omega is basically the square root of this thing, n naught e square by epsilon naught n e, right? So you see that this delta x is basically oscillating, right? Oscillating like a sine wave or a cos wave. And this oscillation frequency is basically given by this omega, which is n naught e square by epsilon naught me, square root of that. Right. So this is what is called the plasma oscillations, right? And these are the oscillations that we see in a plasma, because there will be some violation of charge neutrality at some scales, and those will cause this oscillations, or these perturbations will cause this oscillations. Similarly, so these are the plasma frequency corresponding to the electrons, remember? So as I was saying that, in this plasma, we have to treat the electrons and the ions separately, and both of them will have distinct properties, right? So another property which is distinct for ions and electrons is this frequency, plasma electron frequency. And why is this different is that the masses of electrons and the masses of protons or the ions are very different. Right? So if you see, the masses of electrons are much, much lesser than the masses of ions. So the plasma frequency of the electrons will be much higher than the plasma frequency of ions. Right? So if you have to calculate the plasma frequency of the plasma, it is actually the square root of the plasma frequency of the electrons squared plus the square of the plasma frequency of the ions. But as we just saw that it is inversely proportional to mass, so the W, the plasma frequency due to the ions will be much less than the plasma frequency due to the electrons, and this is the term that will dominate. So the plasma frequency of the plasma will be close to the plasma frequency of the electrons. Right? Okay, so I think that's too obvious, but it was worth mentioning. Right. So now we are going to study what are the criteria of the for a plasma to be called as a plasma. Right? Okay, so these are the main three conditions uh, which uh, which with which we can identify whether a system will behave like a plasma or not. Right? So okay, so the first condition is that omega p tau c should be greater than 1. Right? Second condition is the length of the system should be much greater than the Debye length of the plasma. Because as you saw, the charge neutrality is only valid outside the Debye length, because Debye shielding occurs at a local length scale. Right? Also, this ND should be greater than much greater than 1. Now, what is ND is that it just says the number density inside the Debye sphere, right? Okay, now uh, why is this condition needs to be satisfied? Now we come to the condition that we actually talked about earlier, and from there we can see that this condition has to be satisfied for a plasma. Is that so? You remember we talked about so when we are going from this step to this step, we take the assumption that E phi by kT should be much less than 1. Right? It should be small number. Now that assumption is now coming back, and so basically we are saying that phi uh, should be this value at some minimum radius, right? So this is just the electric potential, right? Now E phi by kT, right? So R is actually proportional to NE to the power of 1 by 3, right? Number density or to 1 by 3. And E phi by kT will then be reduced to this form, right? So now you see that, well, E phi by kT is basically 1 by 4 pi 1 by ND to the power of 2 by 3, right? So, okay, I might not have defined ND, but ND is basically 4 by 3 pi uh, r cube time, lambda d cube, right? So it is the number density within that volume, right? So volume is given by 4 by 3 pi lambda d cube, the d by volume, right? And the number density within that volume, or the number of particles within that volume, not number density, I'm sorry, number density is Ne, and the number of particles within that d by volume is given as Nd. And so if you just put the value of lambda d, which we calculated over here, and you calculate the this thing, so let me just do it again, just so that we don't have any confusion. Okay. Okay, so our condition is that E phi, let me just, okay. So our condition is that E phi by kt should be much, much less than 1. Now, E phi by kt, we calculate it as 1 by 4 pi epsilon naught E square by kt e, n e to the power of 1/3, and lambda d we calculated as epsilon kt by n naught e square. Right. So this is lambda d, this is E phi by kt. Now, nd is basically the number density inside the Debye volume, which is 4 by 3 pi lambda d cube. Right. So this is Ne, and lambda d cube will be, there will be 1 pi and 4 by 3 lambda d cube is epsilon kt by n naught e square whole to the power of 3 by 2. So this is it. Now we just yes. So now if we just put this nd over here, you will just obtain this thing, right? Okay. So that is what the definition of nd is, and this is how we get this thing. Right. So okay. So now you can see from this relation that if E phi by kt has to be much, much less than 1, this nd has to be much, much greater than 1, right? If this denominator is high, then this quantity will be less. So that just means that gives us the condition that nd has to be much, much greater than 1. Right. So what are the consequences of this nd to be much, much greater than 1 is that this plasma frequency, if you see, and this is the collision frequency. So I will not derive this relation, but you can find this relation coming from this Rutherford scattering formula, where you have an ion and there is some electron that is passing by, and what should be the frequency of electrons colliding with this ion, right? And that is given by this formula, and the ratio of plasma frequency to collision frequency, uh, you know, uh, that just gives you this relation. And if nd is much, much greater than 1, then what this says is that the plasma frequency should be, this term, you see that nd is both in the numerator and the denominator, but in the denominator there is a logarithmic relation with nd, logarithmic function, right? But in the numerator, this is a more increasing function. So this will be much, much greater than 1, right? So therefore, this plasma frequency will be much, much greater than the collision frequency. And that is what is actually the first condition. The plasma frequency times the collision time scale, this tau c, should be greater than 1. And that is also what is coming from this relation. Right. So that is another consequence, is that the plasma frequency should be much, much greater than the collision frequency. Right. So this relation you can get in many books, including what I also have in the reference. I mentioned one book, uh, this one, Introduction to Plasma Physics by Garnett and Bhattacharya. So you can look at this book, chapter 2 specifically, where these are derived. So this book is only dedicated to plasma physics. So I think you can also follow this one in the upcoming lectures where we'll be discussing plasmas. Right. So, okay. Now, let's see. Okay. So this we have done. Y and D should be greater than 1. And that also means that plasma frequency much greater than collision frequency. The length scale of the system should be greater than the Debye length. So these are the three conditions uh, for it to be a plasma. Now, another interesting thing that we can observe from here is that we can calculate the ratio of the kinetic energy to the potential energy, right? So kinetic energy, if you remember, it was half mv square, which is proportional to kT, right? K is the Boltzmann constant times T, temperature. And the potential energy is E square by 4 pi epsilon naught R, right? So this is the ratio of the, well, half mv square is equal to kT only when the plasma follows Maxwell-Boltzmann distribution, right? But yeah, anyway, under that assumption, the ratio of kinetic and potential energy can be calculated like this. Right? And again, if you just see that in terms of ND, it can be expressed as this thing, 6 pi ND to the power of 2 by 3. Now, what this says that for a plasma, ND has to be much, much greater than 1, and therefore the kinetic energy should be much, much greater than potential energy, which actually makes sense, right? Because as we discussed earlier, plasma can be formed under very high temperatures, right? And therefore, under those temperatures, the kinetic energy of the electrons or the mainly the electrons will be very high, right? And they'll be moving very fast under those high temperatures. And therefore, the kinetic energy is expected to be much, much greater than the potential energy. Okay. So that is another consequences that we saw. Well, now to conclude the discussion on plasma, we want to also see that at what regime are these quantum effects of this plasma is very important. Right? So, well, we all know the uncertainty principle of Heisenberg, right? Del P del X greater than h cut by 2. Now, del X is basically the length scale system. Like, as I earlier mentioned, it is 1 by n to the power of 1 by 3, right? So it is basically the distance between the two particles in the plasma, mainly the electrons. So that is given by the density, right? Inversely proportional to n to the power of 1 by 3. And the delta P in momentum is basically given as, so a momentum is half mev square, and then square, so momentum is mev and not half mev square. Momentum is mev, and then we square it and take the average and take the square root. So this is kind of an RMS momentum deviation, right? So mev is mev square is actually, well, half mev square is actually kT, right? As we saw from this relation, right? Also when we are calculating kinetic energy. So this will be of the order of kT, right? Right, and 3 me. So 1 me will be taken outside, and you'll be left with mev square. So that mev square equals to 3 kT, and there is me, and then the square root outside. So now, if we just use this uncertainty relation and put the values of delta x and delta p accordingly, we will find that this will reduce down to this relation, right? And simply by rearranging this thing, we can get this relation. Right? Now, what does this mean is that, well, if you see the right-hand side is basically a constant value. This is h cut, constant, Planck's constant, me, electron mass, constant, and this k is the Boltzmann constant, right? So this right side is a constant, right? Now, we want to see that, uh, if this condition is, violated, then we are entering the quantum regime, right? So in that case, uh, we need to have, or as long as this goes uh, close to this value, so in that case we need a very cold plasma. In other words, the temperature of the plasma should be very low, right, for it to go to this value. So this is the condition for classical regime, right? But if this condition is violated, and then it will enter the quantum regime. And how this condition can be violated is by reducing the temperature or by increasing the density, right? So if you have a very cold plasma whose electron temperature is very low, or uh, or the density of the plasma is very high, in either of those cases, quantum effects will become important in the plasma. Okay, but in general, plasmas are generally of very high temperature and low density. But there are some astrophysical cases where uh, this condition might be satisfied, and we could have some cold plasma, which are uh, where quantum effects will be important. Okay, so these are the references, as I was saying. So this, uh, well, the uh, Kundu Cohen, this book, you can have chapter 14. For accretion, this Franking Rayne book, you can look at chapter 3. And for this plasma physics book, as I said, so this would be the most relevant book for the plasma part. So here, this you can look up the part relevant to you. So what I covered today was given mostly in chapter 2, which is just the basic introduction to plasma. But this book is, uh, you know, uh, uh, has many other important topics with respect to plasma, right? And you can also look at this Annam Chaudhary book for plasma as well. But yes, but for the rotation part, so this is also covered in this Annam Chaudhary book for rotation in case of self-gravitating stars and so on. So yes, so that's it for today's lecture. Let me know if you have any questions. Okay, then if not, we'll see you in next week. Okay, so thank you. Have a good night.